So this is a summary video of all the things you need to know about bonding for National 5. So firstly, we need to know why atoms form bonds. It's the same reason why atoms form ions. They do so to become stable. And remember, if an atom does not have completed outer shell, it is unstable. The one type of element that does have stable atoms are your noble gases. They all have a complete outer shell, which makes them stable and is the reason why they are unreactive and they do not form bonds. Every other element on the periodic table has incomplete outer shells and so must do some form of bonding in order to become. Now, there are three ways in which an atom can end up with a full outer shell of electrons. In atomic structure, we looked at how atoms could form ions, and they could either gain electrons to become negative ions or lose electrons to become positive ions as two of the ways in which atoms can end up with a full outer shell of electrons. But in this topic, we'll also see how atoms can share electrons with one another to end up with an outer shell that's completed, but not having to end up charged like an ion. Now, as a consequence of the three different ways in which atoms can become stable, there are also three different types of bonding. We have metallic bonding, where metals are involved and they become positive ions. We have ionic bonding, which involves metals becoming positive ions and non-metals becoming negative ions. And we have covalent bonding, which is typically only non-metals, and they will share electrons with one another. And covalent bonding comes under two categories, covalent molecular and covalent network. So metallic bonding only occurs between metal atoms. The definition in the middle there, you need to know what is metallic bonding, and there will be a definition for every type of bonding. Metallic bonding is the electrostatic force of attraction between positively charged ions, you could call them positive metal ions, and delocalized electrons. Delocalized electrons means that the electrons are free to move around. And we draw metallic bonding as large positive metal ions, the big orange circles there, with a positive charge in them, and then we show delocalized electrons either through the letter E with a negative charge on it or through small circles with a negative sign in them, and we show the delocalizedness of them by having them, the electrons, not being regularly organized, whereas the metal ions are. So the delocalized electrons are free to move, but the ions themselves are. Now, as a consequence of the bonding in metals, they have specific properties. They can conduct heat and they can conduct electricity. The reason for this, and the only reason you need to give, is that they have delocalized electrons, okay? So if you're asked, why does a metal have the ability to conduct electricity? It has delocalized electrons. Two words, that's all you need to write. Our next type of bonding is ionic bonding. So we need to remember about ions from atomic structure. Metals lose electrons to become positive ions, and we've got the example of sodium forming sodium plus ions. Non-metals typically gain electrons to form negative ions, and then we have our example of chlorine going from chlorine atoms to chlorine minus ions. Where we have positive ions and negative ions near one another, we will see ionic bonding happen. Ionic bonding is the electrostatic force of attraction between positive ions and negative ions. There is the saying, opposites attract. This is true for ions. Positive ions like being around negative ions like being around positive ions. Now, the way that an ionic structure forms is that every positive ion can only be touching negative ions, and every negative ion can only touch positive ions. And so we get an arrangement called lattice, where we have alternating positive and negative across rows and down columns, and it exists within 3 dimensions. Now, because of that lattice structure and the fact that you've got so many ions all together, ionic compounds will have really high melting and boiling points because you'll need a lot of energy to break them. In order for a material to conduct electricity, you need to have charged particles that can move. Ionic compounds have charged particles. Ions have charges on them. But when an ion is a solid, they're not free to move, and so it cannot conduct electricity. If you break up the lattice, either by melting it or dissolving it in water, the ions are free to move, and that is what allows ionic compounds to conduct electricity. You cannot say anything about electrons when it comes to ionic compounds conducting electricity. If an ionic compound is conducting electricity, it is because the ions are free to move. Our final type of bonding is covalent bonding, and covalent bonding is mostly just with non-metal elements. In covalent bonding, we're not forming ions. There's no gaining or losing of electrons. Instead, the two atoms come very, very close to one another and share electrons. So if we look at these two chlorine atoms, these both have 7 electrons in their outer shell. When they share 1 electron each, and we count the outer shell for this this chlorine, it has 8, and the other one has 8. By sharing, they've both ended up with a full outer shell, and they've not had to become ions. That shared pair of electrons, held in place by the 2 positive nuclei, is a covalent bond. Now again, we've got a definition. Covalent bonding is the hardest definition. It's the electrostatic force of attraction between 2 positively charged nuclei and your shared pair of electrons. Now it can be represented as on the previous diagram with all the electron shells being shown, but that's actually quite a lot to draw, and it's not often you're asked to do that. We can sometimes draw 1 line for every shared pair of electrons. So we would describe if we have 1 line as being a single bond, but some molecules like oxygen will have 2 bonds between the 2 oxygen atoms. That's because they're sharing 4 electrons each. The most common way is by only showing the outer shells. Now in this diagram, they've got the shells touching one another. You can also have them overlapping with one another. And then you put the shared pair of electrons in the shared area. Okay? So you can either have the 2 atoms overlapping and you put your shared electrons in the middle, or just have them touching and then the electrons have to be on the line. When it comes to covalent compounds, there are 2 forms of covalent bonding. We have covalent molecules, which are small and have a fixed formula and size, and we have covalent networks, which are enormous and do not have a fixed size. So covalent molecules, examples of which are methane, water, carbon dioxide, all of the diatomic elements, which we'll talk about in a second. And any of the molecules from Unit 2 are covalent molecules. So alcohols, alkanes, alkenes, etc. They are small and discrete. Discrete means that the molecule exists isolated from other things. Now, covalent molecules themselves have very low melting and boiling points, and so they tend to be liquids or gases. Now, if you're asked why does something have a low melting boiling point, this is the answer. There are strong bonds between the atoms, but weak bonds or weak forces between the molecules. So the diagram at the bottom is actually water. Those water molecules, the white is the hydrogen, the H2, and the O is the red. The dashed lines are the weak bonds or forces between the molecules. They can easily be broken, which allows ice to turn into water or water to turn into steam, but the molecules themselves, the H2O, is never broken whenever you're melting it. It stays the same. So that's because there's strong bonds between the atoms which keep the molecules together, but weak forces between the molecules which allows the molecules to be separated further away from one another, which is what melting and boiling is. Now, when it comes to covalent molecules, you need to know that there is a list of 7 diatomic elements, and you can remember it as Hinkelbroth. You can be asked to draw the outer electron shell overlapping for any of these diatomics. They do not all have the same number of bonds. So in hydrogen, each hydrogen has 1 electron, so when they share, both electrons are being shared in the middle. Nitrogen is the most difficult one. Nitrogen has 5 electrons in its outer shell, and so it needs 3 more. The only way for nitrogen to get 3 is by sharing 3 electrons from each nitrogen in the middle, and we would represent that as a triple bond. Oxygen has 6 electrons in its outer shell, and so oxygen has 6, so it needs 2. And that's why you can see that there's 2 circles and 2 crosses. And we would represent oxygen as a double bond for that situation. For fluorine, chlorine, bromine, and iodine, they all only need 1 electron each, so they would have a single bond, just 1 dot and cross shared between the 2. So fluorine, chlorine, bromine, and iodine, all very much the same with a single bond between them. Nitrogen and oxygen are the ones you need to be cautious of. Nitrogen has a triple bond, 6 electrons in total being shared. Oxygen has a double bond, 4 electrons in total being shared. There are other molecules that you need to know the shape of and can be asked to draw diagrams for. You have molecules like hydrogen fluoride, or any one where it's 2 different atoms, will usually have just 1 bond, one covalent bond, and it will be linear because they make a straight line. Molecules like water are angular and they have a bend in them. Ammonia, that's forming 3 bonds, forming 3 bonds to hydrogen there. It is trigonal pyramidal. Trigonal means it's based on a triangle, pyramidal because it actually sticks upwards, it's not flat. And methane, where you've got 1 atom forming 4 bonds to hydrogens, that is tetrahedral. So you do need to know how to draw the outer diagram, the number of bonds, and you need to know the shape of these. So spend the time learning the shapes of these molecules. The only other molecule you need to know the shape of is carbon dioxide. And carbon dioxide is a really difficult one to draw. It has 3 atoms, but it is linear in shape. The reason for this is because carbon has 4 electrons and needs 4, so needs to share 4. Each oxygen has 6 and needs 2, so we'll share 2. Carbon needs 4, oxygen needs 2. The only way for carbon to get 4 is for you to have 2 oxygens. The oxygens go on the outside Each oxygen shares 2 electrons with a carbon, and the carbon shares 2 electrons with each oxygen. This diagram is the hardest one to draw, so I would spend the time to learn it. That was covalent molecules. Next we have covalent networks. Now covalent networks, we also have this word lattice in there. Lattice just means having the same thing repeating over and over and over and over again. Covalent networks have thousands, if not millions, of strong covalent bonds, which make them really tough to break, and you need a high amount of energy in order to melt them. There are 3 examples of covalent networks that you need to know. The first is silicon dioxide, which is a chemical found inside sand. It is not sand, it's one of the chemicals in sand. It's also one of the chemicals in glass. SiO2, silicon dioxide. The other 2 are both forms of the element carbon. Now we have graphite on the right-hand side. Graphite forms layers, and then on the left-hand side we have diamond. They are very different to one another. Graphite is special. Graphite has delocalized electrons. And because it has delocalized electrons, it can conduct electricity. Most covalent things, because they don't have ions and they don't usually have electrons in them, cannot conduct electricity at all. The only covalent network that can conduct electricity that you need to know about is graphite. Slide here is a summary of the types of bonding. So metallic compounds typically have high melting and boiling points, and they can always conduct electricity. Ionic compounds have high melting and boiling points because they have an ionic lattice, lots of ionic bonds altogether. They cannot conduct electricity when a solid because ions cannot move, but when you dissolve it or melt it, it can conduct electricity because the ions are free to move. Covalent molecules have low melting and boiling points because there are strong bonds between the atoms but weak bonds between the molecules. They do not have any delocalized electrons or ions, so they can never conduct electricity. Covalent networks have high melting and boiling points, very high melting and boiling points, because you're needing to break thousands of strong covalent bonds. They usually cannot conduct electricity because they do not contain any ions or delocalized electrons. The exception is graphite, which does contain delocalized electrons. That has been a summary of all the things you need to know about bonding for national facts.